You hear me now? Better? All right. So welcome to the course in Information Processing and Learning. Um, my name is Noga, for those of you who don't know me. I'll be your TA this semester. If you have any problem, you can contact me. This is my email. Um, at Fuji, you know how it goes. If you have any questions, just write me an email. Reception hour by appointment, so please write me and we'll find a time to meet. Um, the first lecture of the course would be next week, not today. The course is this year, the lecture is Naftali Tishbi. So next week we'll give an introduction to the course, and that will be the first lecture. Today and tomorrow we'll do a quick probability recap. So for those of you who feel very comfortable with probability, so you don't have to stay. Just wait a few more minutes after I'll say everything, all the administrative things. But if you want to stay anyway, you're very welcome. There will be a weekly exercise in this course. Some of the exercises will require programming, so MATLAB, Python, whatever you prefer. You'll have to submit all the exercises through the course Moodle. So you're encouraged to use Leak or LaTeX or any LaTeX editor you like. If you do want to handwrite your exercises, so just scan them and upload. And the final grade will be 25% exercises, the average of the best n minus 2 out of n exercises, and 75% the exam. Any questions about administrative things? Yeah, it will be a weekly. Even if you think you know the course material, or at least part of it, I strongly recommend that you attend the lectures at least. One of the main things of this course is to integrate different fields, information theory and machine learning, so you'll probably see new, even if you know some of the material, you'll see new connections that you didn't see before. So I strongly recommend that at least everyone come first lecture next week. Okay. So let's start with probability. Yeah.
Is there a textbook for this course?
There is one in Hebrew that doesn't contain all the material, but most of it. I'll try to upload some references to other textbooks that may be helpful. If I don't do that, just remind me. Okay. Anything else? Questions? If you feel free to ask questions during the class. If you lose me, just raise a hand and tell me that I should slow down or something. So okay, let's start with probability. So the notion of probability is related to uncertainty we have in the world, right? We don't know, for example, whether I pass the course or not, what will be my final grade. These are all questions that we don't know the answer for, but we usually do know what is the set of possible options, right? Even if we don't know what will be the actual outcome. So this is the first ingredient in a probabilistic model. It's the sample space, right? Sample space, and we usually denote it by omega. So let's start with a few very simple examples. So if I toss a coin, what is the sample space? Toss a fair coin? Heads or tails, right? So heads or tails. Now if I toss a coin until the first time heads comes up, so what is the sample space?
Natural numbers.
Exactly. So it will be sequence of, let's say, n minus 1 tails, and it ends with the heads, right? And n could be any natural number, right? Um, if I throw two dice, then right. Um, and what if the dice are indistinguishable? So I throw two dice, but I don't know which is which. Right. So here, this is like all pairs of I and j, let's say, where I and j are numbers, integers between 1 and 6. And let's say this is the result of the first die, and this is the second. But if I can't distinguish them, okay, so for instance, if I got 1 and 2, or 2 and 1, if I can't distinguish between them, this is the same outcome, right? So we want to put this together, and we just decide to denote this outcome by either one of those. So it will be um, all pairs of I and j, such that I is, let's say, less or equal than j, and they are both between 1 and 6. Okay? So here we have two options, right? Here, how many options? Like, right, but it's countable, right? And here is also finite. We also have, it's also a possibility that, um, for example, if you go to the post office and you don't know in advance how long you will have to wait, so what will be the sample space in that case? So any time between 0 and infinity, right? So this is a continuous sample space, right? So there are several options, and we'll see that the mathematical treatment of probability in the discrete cases and the continuous case is a little bit different, but we'll try to skip over it and handle everything. Okay, so how do we define probability over these sample spaces, right? For each event, we want to assign a number that quantifies our uncertainty or our knowledge about the possibility of seeing one of these outcomes. So if we have a fair coin, so what is the probability function? Just each outcome has a probability of half, right? What is the probability here? If it's a fair coin and I toss it until I see heads, till the first time a head comes up. So what will be the probability of an outcome in this sample space? Hmm? Well, each outcome here has some probability to occur, right? So let's say I have, right? So I have a sequence of n tosses. Let's say it's a fair coin to the power of a, right, right. So it will be exactly, um, right? What will be the probability of a single outcome here? Right. And here, there are 20 options, right? But not they don't have all equal probability, right? So it depends. It depends if I equals j or not. Okay, never mind. So these are some examples. Let's define the probability model. So we want to give a mathematical definition of the probability function. So we'll start first with the discrete case. Okay, so discrete probability discrete probability model. Sorry if my handwriting is terrible, and I apologize. So it consists of a discrete sample space and a probability function. That is a function from the sample space to the interval 0, 1. And we require that the probability function would satisfy two conditions. So it has to, for each outcome in the sample space, we require that the probability of the outcome would be non-negative, and we required normalization. Okay, so if you sum over all the events, you get 1. Um, okay, so now let's say that someone rolled 2 dice and rolled a die and told you that the outcome was an even number. Okay, so now the outcome, it's not a single outcome in the sample space, right? But you do know that the outcome is is either 2, 4, or 6, right? So it's an element in this subset. Okay, so sometimes we want to talk about events and not about single outcomes. So we define an event. Okay, so an event is just any subset of the sample space. Okay, so just a quick reminder. Um, uh, the complement of an event A, we denote it like this, or sometimes it's also denoted as A bar, same thing. It's basically the event that A did not occur. So it's are you everyone familiar with these notations? Okay. Second. Okay. We say that 2 events are disjoint. Disjoint. If their intersection is empty. Okay. So. Okay. Maybe it's obvious, but omega is also an event. The empty set is also an event. If we talk about intersection between events, it's also an event. And if we talk about union of events, so this is also an event. Okay, so this is just a quick reminder about events. Okay, so what happens in the continuous case? You know what? I want in the continuous case. Questions? All right. Okay. Anyone still needs it? Okay. What happens in the continuous case? So, I'm sorry. Before we go to the continuous case, the way we define here probability is just for single outcomes, right? But we can easily extend this function to any event. Okay? How do we do that? We simply define the probability of event A as sum over all outcomes in A of the probability of all outcomes in A. Okay? So we can out of this function we can construct a function that is actually this function is from the power set, all subsets of the sample space to the section 0, 1. Okay. So what happens in the continuous case? Things become there's some mathematical subtleties that we need to take into account, and we can actually it's not possible to define a probability function in this way, but we'll not go into this in this course. But I'll just, for completeness, I give a more general definition of a probability function. So basically, we require that in continuous case, or actually in general, we require that the probability function will obey 3 conditions. First of all, the first one is that the probability of the empty set is 0, that the probability of the sample space is 1, and for if A1 to AN are disjoint, mutually disjoint, meaning that every subset here is of these events is disjoint, then the probability of the union is simply the sum of probabilities. Okay. Actually, if you want, if you're curious, it's very easy to show that this probability function also obeys these three conditions. So we can show that at home if you want. Okay. Do you need anything? Can I erase this part? Okay. So now that we defined the probability of an event, um, so let's say A and B are two events, okay? And we know how to define the probability of A now. Now we can ask how much will the probability of A, how much will it change if we know that another event B had occurred. So to answer this question, we define the conditional probability. And conditional probability. And probability of A given B, it's the probability of A and B, the intersection between them, divided by the probability of B. Okay? Why is that? If we know that B occurred and we want to know what is the probability of A, so we know that the outcome will be some event in the intersection, but we need to take into account also all other outcomes in B that did not occur. Okay? So it's easy also to verify that if you define this probability, then it's also a probability function. This definition. The total probability theorem states that if you have an event A1 to AN that are mutually disjoint but their union is the entire sample space, then for any event B, you can write the probability of B simply as the sum I of the probability of B and AI, the intersection between them. So if we use the definition of the conditional probability, we can simply get that it's the sum over the probability of B. Do you see here? It's too low? Or do you notice already? B given AI times the probability of AI. Okay? So far, so good? You know all of this? You don't know? If you have any questions, please ask them. Okay, so not always, if we know B, it doesn't necessarily tell us anything about A, right? Sometimes knowing B will change the probability of A, and sometimes it won't. When it doesn't, when B doesn't give any new information about A, then we say that A and B are independent. Okay? And the definition of independent events are if the probability of A and B equals the probability of A times the probability of B. Want me to change the marker? Um, okay, just one thing that you should know that if two events are disjoint, okay, it does not necessarily mean that they're independent. Okay, so an easy way to see that is that if they're disjoint, that means that the probability of A and B, this is simply the empty set, so it should be 0 on the one hand. But if they're independent, then it also should be PA times PB. So in fact, two disjoint events are independent only if one of them has 0 probability. Okay. Um, all right. So if we know, just a minute. Sorry. Um, okay. So if you take this and that definition, it's easy to see that two events are independent if the probability of A given B equals the probability of A. Okay, so knowing B does not give any new information about A, and usually we call this probability a prior probability, and this probability a posterior probability. Okay, so this is our prior knowledge of A before we know anything, and this is our knowledge of A after we know something new. But if they're independent, then we don't. They're equal, like prior and posterior. But what happens in the general case? So this way. Um, so in the general case, we use Bayes rule to to um, uh, Bayes rule gives us a way to update our knowledge about A after we know something new. So Bayes rule um, states that the probability of A given B equals the probability of B given A times the probability of A divided by the probability of B. Okay? So here we have the prior, and here we have the posterior. Okay? So basically, it's a way to update our knowledge, right? It's very easy to prove this just from the definition of the conditional probability, because if um, um, sorry, okay, so just to prove this this formula. So on the one hand, we have um, right. This is just from the definition of the conditional probability. But on the other hand, we also have um, that the probability of A and B equals the probability of B given A times the probability of B. Okay. So if you just equate these two parts, and you get Bayes rule. Okay. So let's do a simple example. Is it too slow for most of you? All right. So you want to skip the example? All right. Hmm? You want the example? All right. I said at the beginning that it will be a probability recap for those who are not comfortable with the probability. So if you're comfortable, you don't have to stay. It's all right. But do come to the lecture next week. Okay. So suppose a probability of contracting a disease is 1 over 1,000, and we have a test to check for this disease, which with a probability of the test being correct um, um, correct is 0.9. So this is also for false positive and for false negative. Sorry. Yeah. Okay. So um, now suppose a patient took the test and the test turned out to be positive. Yeah. נכון. נכון. תודה. Um, okay, so this is the probability of being sick. This is the probability of the test being correct. Okay? So suppose the patient now took the test and it turned out to be positive. So what is the probability that the patient has actually has the disease? Okay, so you want to help me? Yeah. I can't hear you. Yeah. So this is like the prior probability of being sick. This is our knowledge about the test, and now we're asking, after you took the test, how much the prior changes? Uh, no, yeah, this is what we're asking. Okay. I can't hear you? Right, of course. So we defined A as the event that the person is really sick, and sorry, and we defined B as sorry, as the event that the test is positive. So PA is 1/1000, right? Now what is PB? Okay, what is the probability of B? 0.9. This is the probability of the test um, being correct. This means that the probability of um, B given that the person is sick, right? Times the probability of A, and for both cases, right? So it's also the probability of the test. Let's say test saying that 1 is sick and 0 is healthy, right? So sorry, yeah, this, okay. And it's also the probability of not B given not A times the probability of not A. But we're asking here what is the probability of B, right? So we can use the total probability theorem. Simply states that probability of B is the probability of B given A times the probability of A plus the probability of B given not A times the probability of not A, right? So basically this, I don't have much room. So it's 0.9. Okay, and now we're asking what is um, the probability of A given B. So it's using Bayes rule. It's the probability of b given a times pa divided by the probability of p given b, which is simply uh, the probability of a is 1 over 1000. Probability of b given a is 0.9 divided by pb, which we wrote there, and you can verify at home that it's about 0.009. Okay. Um, all right. So in many cases, so far we talked about events, but in many cases we are interested about some numerical function of an event, not the event itself. For example, event could be some real object in the world. For example, a person. If you pick a person at random, but sometimes you're interested maybe what is the age of this person, or sometimes you want to know just if a certain event occurred. So you want to define a variable that says 1 if the event occurred and 0 otherwise, which is like an indicator variable. So in this case, we want to talk about random variables. So let's define the random variable. Okay.
רגע, מה כאילו השורה התחתונה של הדוגמה הזאת שהבדיקה לא שווה כלום? בגלל שהנבצרות שאתה באמת חולה, אפילו כשהבדיקה הייתה כל כך קטנה?
Some people don't understand.
Yeah. It basically means that
I don't speak English.
it basically means that if you have a test that probability of being the probability of the test being correct is 0.9, it's not enough. Yeah, right. Don't freak out. You can probably trust what your medicine. You should be careful. Okay. So suppose we have a probability model. So it's a sample space and a probability function. So we define the random variable as a function x from the sample space to, this is a real value random variable. So this mostly we'll discuss only these kinds of variables in the course. It's basically a function from the sample space to the real numbers. Okay, so it's worth noting that any function of the random variable is also a random variable. For example, x to the square is a random variable. If x is a random variable, sine x. Okay, you'll see more examples, many more examples in the course. Okay, so how can we define the probability of the random variable? Okay, so for example, if we know, I don't know, that x equals 1, this is an event. Okay, just for example. So how can we define the probability of it? So first of all, once again we'll do a different treatment for the discrete case and for the continuous case. So in the discrete case, we can define the probability mass function. So the probability of the event x being equal denotes by small x a particular value, and by large x the variable itself. It's simply sum over all outcomes in the sample space. I'm sorry, no, that's not true. It's simply sum over all outcomes such that x of that outcome equals a particular value from the probability. Okay, this is pretty straightforward. Usually we'll just write px. So for example, okay, we'll do a very, very simple example. If we have just head and tail, all pairs of heads and tails, right? There are four options. All options have equal probabilities for pair coins. So let's say we define the random variable x, that is the number of times heads came up. Okay? So what is the probability of x? Or a particular value of x? So we have three options, right? X could be 0, it could be 1, or it could be 2. Right? So what are the probabilities here?
Quarter, quarter,
Quarter and
half and quarter.
right. Everyone follows? Pretty straightforward. Okay, so what can we do in the continuous case? Okay, so we say that the random variable x is continuous. Continuous if we can write the probability of x being in some subset where d is a subset of the real numbers. So you can write it as an integral over some function dx. So if we can express the probability of x in this way, we say that x is continuous, and in fact this function f, we call it f is the probability density function, or the PDF of x. Okay? So in particular, we can think of cases where p is some interval, okay? A and b in R. So just some intuition about this. Okay, so just some intuition about what this means. So suppose we have a sample space, okay, and here is the event x is in A, B. This is an event in the sample space, okay. So we define some function that that assigns to this event some probability. So this is fx is x, for example. Let's say there is some probability function, density function, sorry, d. Okay, so it's basically the area beneath this function. Okay, so basically the density function basically models for us how to take the probabilities from the sample space and we map them to probability to some probability function over the real values, okay, and the real numbers. So what do we need to require from f in order to have a probability function? We need that we need to require a few things. First of all, fx should be non-negative. We require normalization, so to integrate from minus infinity to infinity, then it should be equal 1. Okay, so these are the two requirements. Two things that we should know. First of all, f itself is not a probability. Okay, it's a density function. So to get a probability from f, you need to look at the small interval. So just intuitively, in the continuous case, p x equals some small value x plus dx. Okay, so if dx is a very small interval, then we can approximate this by fx dx. Okay. In general, the density function could be in general. Um, fx could be larger than 1. Okay? So you get a probability only if you multiply with that small interval. Is this clear? This is usually the point where many students are confused. Okay. Just one thing to note, if we define it this way, okay, so what will be, in this case, what will be the probability of x being in the interval AB? Just to integrate between A and B or with the density function. Okay, but it doesn't matter here if you include the borders or you don't include the borders. Okay? Right. Okay. So we talked about the probability mass function for discrete variables, and we talked about density function for continuous variables. We also want to have a function that we can use for both cases. So this is what we call the cumulative distribution function, or the CDF. Okay, and basically define it as the probability of x being less or equal than x. Okay, so what is this in the continuous case? Just the continuous.
The CDF?
Mm-hmm.
The CDF means? What does it mean?
Cumulative distribution function. Okay. So in the continuous case, it's just the interval from minus infinity to x, to this particular value, the density function. What is this in the discrete case?
Summation.
Mm-hmm. Over what? Um, over all possible values of k that are smaller or equal than x, and the probability of. I'm sorry, this should be some other. Okay. So some properties, I'll write it here. So first of all, the CDF is monotonically non-decreasing. Okay. Monotonically non-decreasing. Okay. If you take the limit when x goes to minus infinity, what will that be? Hmm?
Zero.
The limit is 0. Right. And if you take the limit x goes to infinity, it will be 1. for discrete random variable. So it will basically be a step function, right? Because you have discrete values and you sum over discrete values, so it is a step function. And for okay, so for continuous random variable, it depends how the density looks. And two things that I didn't mention. First of all, we usually we denote by some upper bigger x, the support of x, which means the values that x can get with a non-zero probability or non-zero density. And another thing that I didn't mention before is that the density function does not always exist. Okay, so can you think of a case where the density doesn't exist? And you don't have a density function? You have a random variable. Okay, for example, if you have, let's say, sample space is the numbers, so define the random variable that assigns to every outcome, every number, 0. And this is a valid random variable, but it doesn't have a density. Okay, I think we can take a break. אינטרוול קטן סביב F. אז נגיד אתה לוקח פה אינטרוול מאוד קטן, נגיד A פלוס דלתה D, כן? אוקיי? ואתה רוצה לדעת מה ההסתברות שתקרה X פה. אז F של X זה הגבול של הדבר הזה, ש-D, אפשר לשאול את זה.
זאת אומרת מצד אחד שכאילו גם נצטרך לנסות אבל אם נקודה כבר שווה לאחד
כאילו, קח את ה...
זה של X זה לא גובה שזה כן
כן, F של X זה הגובה של... זה בדיוק הפונקציה.
אוקיי, אז אם באמת נקודה כזאת שווה 5 אז יש חייבים להיות מספרים שליליים זהו?
לא, לא יכול להיות. אמרנו ש-F של X זה הגבולה
אתה לא מבין
בוא ניתן לך דוגמה לא קשורה להסתברות, כן? יש פונקציה זאת 1, 2, 5
יוני ועידון.
היא לא רציפה, אבל יכול בין 1 ל-2 היא הפונקציה הקבועה 5 ומחוץ ל-1 ל-2 היא 0. זה לא קשור בכלל. מה האינטגרל של הפונקציה הזאת? 5 יכולים להעביר אינפורמציה, נגיד איזה נושאים יש לנו אינפורמציה שעוברת במוח, כלים שעוברת במוח, זה הכל דברים שתסיימי את הקורס ותהיי מסוגלת, יהיה לך כלים להתמודד עם שאלות האלה. יש אינפורמציה לא, אבל יש הרבה כלים שאנחנו יכולים להשתמש בהם. יכולים ללמוד דברים, מודלים
Capacci ma Terencio le fai segno nella volta la casa dove vai su
Okay. Let's start. Can you hear me better? Because I think I have to change the battery. Can you hear me? I think it's not working. Is that right? If you in fact have problems hearing me, that you can either move to the front or just tell me and I'll try to speak louder. Okay. So the first hour we talked about the density function and the cumulative distribution function. So let's see an example. Um, okay, let's take a very simple example. So suppose x is a continuous random variable that is uniformly distributed on the interval in some interval between a and b. So we denote it this way. Okay. So what does it mean that x is uniformly distributed in this interval? Okay, so the density means that the density of x is some constant for x in this interval and 0 else. Okay? So what is c?
1 over c minus a.
Okay, so let's show how do we know that? So we said that the integral from minus infinity to infinity of f should be 1. Okay? So this is simply the integral between a and b of c, which is c by times by b minus a. Okay? So we get that c equals 1 over c minus a. Okay? Everyone follows? What is the CDF? So what do you need to do to get the CDF? I'm sure you all know the answer, but the point is how to find it. So f of x is the integral from minus infinity to x of the density. Okay, so in this case, it's 1 over by minus a. The integral, I'm sorry, it should be here
interval. Okay? So then it equals x a minus a. So the density, the CDX, I'm sorry, of x is x b minus a if x is in the interval. It's 0 if x is smaller than a, and it's 1 if x is larger than b. Is clear? So maybe we can, just to illustrate this, the density function looks something like this. We have here a, b, and this is 1 over b minus a. Okay, this is the density, and the CDF would look something like this. So here is 1. Okay.
Should be x minus a there. X minus a over b minus a.
Right. Okay, so far? Questions? Do you hear me? So now we want to talk about cases where we have 2 or more random variables, and we want to describe their joint probability or a joint distribution. So once again, it will be a little bit different in the discrete case and in the continuous case. And once again, it won't be a problem for us. Do you still need this?
Will you upload this to the model?
I'll try. I can't promise, but I'll try. So in any case, you can find these things in any probability textbook. By the way, during the break, a few people told me that Wuti is, you can get a copy of the course book from Wuti, so it's in Hebrew. Those of you who speak Hebrew can take it from Wuti. Do you still need this? Sorry. Okay, so suppose x and y are 2 random variables. So in the discrete case, we say that the joint probability of x and y, okay, x and y, is the probability of the event x equals x intersected with the event y being equal to some value y. Okay, and this is for all x and y. Okay, this is pretty straightforward. But in the continuous case, once again, we cannot define it in this way. So we define the joint PDF. This way. So the probability of x being in some subset dx and the probability of y being in some subset dy, just the integral over x over the domain of the subset of x and integral over dy of the joint density function. This is the joint density function. so we require that both of these functions would be normalized. Okay, so if we sum in the discrete case, we require that if we sum over all x and y, the joint distribution, we would get 1. In the continuous case, we require that the integral from minus infinity to infinity would be 1. Okay? So suppose we have a joint distribution, either a joint probability or a joint density. We can ask from this we can obtain the probability or the density of the single variable. This we call the marginal. Okay, so the marginal is simply so let's say fx. If you have the joint densities, we can get fx by integrating over y. So fx y dy, and in discrete case, you get px to sum over y. Okay. Just something about the notation. I wrote here fxy and fx, right? And in general, we can also talk about the marginal of y. So these three functions are basically different functions. Okay, so if we want to be very precise, we should have written fx and fxy and fy to remember that these are all three different functions. But just for simplicity, we don't write it, but remember that these are generally different functions. Okay, so this might be a bit confusing for someone who didn't see it before. Okay, so in the same way we can also define the joint cumulative distribution function, the joint CDF. Okay, so in the discrete case, it's just in the discrete case it's pretty, I think, straightforward. In the continuous case, it's defined the joint CDF simply as the probability of x being less or equal to some value and y being less or equal to some value. And this is the integral from minus infinity to x and integral from minus infinity to y, the joint density function. Okay. Okay, so when we talked about events, we talked about conditioning, the probability of one event conditioned on another event. We can do the exact same thing with random variables. So in the discrete case, we can talk about the conditional probability. In the continuous case, we can talk about the conditional density. Okay, so the conditional probability of x being some value given y is c x being x, y Okay, so just for simplicity, just a matter of notation, we usually write this as px. Okay, so this is just a matter of notation. It's sometimes confusing, but it's good to remember. I'm sorry, this is y. So you should remember that when we write it this way, and this is the notation that we'll use throughout the course and reviews, we mean this. Okay, so this is an event, this is an event, this is an intersection of two events, and this is another event. And for the density function, so the conditional density, so now, yeah, the joint density divided by the marginal. Okay, so this is the marginal of y. Okay, so let's do just small exercise. Suppose we have two random variables x and y, and we define another random variable z that is x plus y. Okay, so what will be the density function of z? Okay, so I'll give you a hint. For every value of x, suppose there are two real values, both of them can get any real number. So if we know x, then we need to sum over all values of y that are, so to find what is the density of z, right, we need to consider all possible values of y such that y equals x minus z. Z minus x. Okay, so we basically integrate from infinity to infinity. That's x. This is the density of x, and the density of y, and z minus x dx. Sorry for my handwriting. Is this clear at this point?
X and Y are uncorrelated?
Suppose they're independent. Yeah.
Independent?
Yeah. Right. Right. I didn't say that, but we say that independent random variables, same as we defined as for events or independent, means that for all values x and y, either p x y equals p x p y, or in the continuous case, we define this for the density. Okay, so now we have random variables, we can ask some properties of the random variable. For example, what is the expected value of the random variable, or how much is it, what is the variance, how much it's spread across the course. So let's define first the expected value, or a mean. Sometimes requires a mean. So it will be in this case we just sum over all values of x, just the weighted average of the possible values of x. In the continuous case, it's will be an integral. Okay, so from infinity to infinity. Okay, so some properties of this. We say that any function of a random variable is also a random variable. So what will be for any function of x, we can also calculate the expected value. And it will simply be, I'll write just for the discrete case, but the same for the continuous. Just will be sum over x, the gx times the probability of x. And what will happen if g is just a simple, just a single, just a constant function? So if gx is just some constant, then we get that it's pretty obvious that the expected value is also the same constant. Another property of the expected value is that it's linear. So it's very easy to show. I'll leave that for you to show at home. So if we have the expected value of ax plus y, where x and y are two random variables, it's a times the expected value of x plus the expected value of y. Okay, so you can show that at home. And also, if x and y are independent, then the expected value of x times y is the expected value of x times the expected value of y. This is actually true if they're uncorrelated. Never mind, we'll talk about it in a minute, but it's not true in general. So it's also very easy to show. I can leave that for you to show at home. Okay, so now we want to define the variance of the random variable. So the variance of x is defined as the expected value of x minus its mean to the square. Okay, and we say that the standard deviation is the square root of the variance. Okay, so some properties. So first of all, it's very easy to show. I'll leave this. You can verify this at home as well. That the variance of x is the expected value of x to the square minus the square mean, the mean. Okay. Since this is an expectation, we take an expectation over a non-negative function, so we also know that the variance is non-negative, and in fact it's 0 if and only if x is a constant. Another thing, that if we take a linear function of x, so ax plus b, so the variance of this is a to the square times the variance of x. Once again, it's very easy to show from the definition. And if we have, I'll write here, I'm sorry. So if we have two random variables, so the variance of the sum is the variance of x plus the variance of y plus twice the covariance of x and y understand so far? Um, okay, just one thing, if we have um, more than two random variables, let's say x1 to xn variables, and if they are all independent, so the variance of x1 of the sum, right? The variance of the sum is the sum of the variances. Once again, this is not true in general. This is true only if they're independent or actually uncorrelated. Never mind. So let's do just a simple example. Okay, so once again, let's take x as uniformly distributed over the interval AB. So let's calculate the mean and variance of x. So what will be the expected value? What integral should I write here?
Summation over x times its integral.
Right, but it's a continuous random variable, so we write an integral, and we should write from minus infinity to infinity, but since the density is only non-zero only in the interval, so I write from a to b, x times the density of x, right? But the density of x we already calculated. So this is just 1 over b minus a in this interval. So basically CA, which is b plus a divided by. Okay? Okay, so to calculate the variance, we can use this formula. So we already have the expected value. So we want to calculate this the expected value of x to the square. So um, so it's the integral from a to b of x to the square times 1 over b minus a. So this time we have 1 over 3 b minus a, x to the third. Okay, and I leave you to check at home that it's b minus a to the square divided by 12. It's very easy to verify. Okay. So we saw here the covariance, and I didn't. Let's talk about a few properties of the covariance. Property. expected value of x times y minus the expected value of x times the expected value of y. Okay? So if x and y are independent, then this will equal this, and the covariance would be 0. Right? Is that I erased it already, but you can easily verify this. So in general, this could be 0 also when the x and y are dependent. So the covariance being 0 does not imply that x and y are independent. And we say that when if x and y are uncorrelated, when the covariance between them is 0. Okay? Also, the covariance is symmetric. So covariance between x and y is the covariance between y and x. It's also if you take a linear combination, so ax plus b and cy, covariance between a linear combination of x and a linear combination of y. So it's a times c, the covariance between x and y. And the covariance between x and x, what is that? The variance. Okay. So many times we want to have a measure of how much x and y are correlated. Right? So if they're uncorrelated, the covariance is 0, but if they are correlated, you want to measure how much. And for this, we define the correlation coefficient between x and y. So the correlation coefficient, we denote it by rho. It's the covariance of x and y divided by their variances. Okay, so some properties of correlation coefficient.
Where were the variances?
Right, inside. Okay. So just some properties. This is always between -1 and 1. Okay? And if correlation is 1, okay, if and only if actually, y and x are a linear combination of each other. So we can write y equals ax plus b for some a and b. Okay, any questions so far? Okay, so we talked about discrete and continuous random variables. We talked about cases where we have two random variables, and how we condition them, and how we compute the joint probability, joint density, the marginals, etc. But what happens when we have many random variables, more than two? So let's say all right. Okay, so suppose we have sequence of random variables, okay, and with joint probability or density, doesn't matter. So when I write this, from the context, you should infer whether it's a probability or a density. Depends. But you should know it from the context. At this point, for this, doesn't matter at the moment. So sequence of random variables, and we want to talk about their joint distribution. So in general, it depends, but there is one case where, not one, but a very useful case when this joint distribution is easy in a sense. Um, we can express this joint distribution in a relatively simple way. So this we call this a Markov chain, and it's actually very useful. Talk about Markov chain, you can see it in many different fields. But to define it, so suppose we have sequence of random variables. We say that they form a Markov chain if their joint probability obeys the Markov property. So what is the Markov property? It's for all I between 1 and n, p xi given x1 xi minus 1 equals pxi condition on the on xi minus 1. So what this means basically, we can always write this probability. We can always write px1 to n. We can always write it as px1.
Could you please not write the winner?
Okay. Okay. So we can always write this px2 given x1, px3 given x1 and x2, etc. This we can always write. Okay, this is always true. But what the Markov property says is that if the probability distribution of xi only depends on the previous random variable. Right? So sometimes we denote it as x1